Yeah. But how do I like communicate with all four of you? No, I thought like in that. Oh, on the side. Yeah, like how do I like I don't know, like thank you for doing this. Okay, like you run this road. It's like on this side. Why did I lose one okay, now I got it. Here's mine.
Hello.
All right. So, hello, Mas. Hopefully you can hear us.
We can hear you. What about you guys? Can you hear us?
Yeah, we can hear you, and we can even turn the volume even louder. We can hear you very well.
Excellent.
Perfect.
We have 6:57. We're just going to wait a few more minutes, then we can start.
No problem.
You can picture, yeah, sure, absolutely. Okay. Perfect. And then I have more to share. Yeah. Yeah, take pictures. Wait, what's happening? The organizers are taking a picture over there. Okay, so we should get started in a second. She's kind of bad. We need to get started on each side just ourselves. 2 more minutes. Yeah. That's fine. All right, so because it's 6:59, I think we should get started, don't you think? So actually, we didn't have all the presenters. So see, that was good that we waited.
Nick also has joined, so we have
Now we have the
me and yep.
we have everybody, so we could get started. So 6:59. Let me just stop sharing, and I'm going to briefly introduce ourselves here. So let's see. I guess do you see us? What you should see
I
right now.
can see you like
This would be me.
Yep.
Yeah, we see the podium.
You can see the both of us. Okay, that's good. Well, all right. So then I want to say that this is an event organized by the Engineering Club, as well as QuTE or QuTE, depending on when you're asking. That's quantum technologies for everyone. So I guess the people that I'd like to introduce as organizers would be, this is Shane Sparks. He's the director of outreach. We have Dmitry Volkov, who's the president of QuTE. We have Rabia Gafour, and she's the president of engineering. And from the marketing department who did the poster, we have, why don't you, what was that? Paulina. Very good, Paulina. And So we are now ready to get started. Now, what I'm going to do is I'm going to let the presenters introduce themselves in a second. We're going to share the screen again and say that what you should see at this point is essentially the poster that we have for today. The proceedings for online proceedings for this year are basically here. And I send a link to this. This is things that have happened up until today. And when we find a poster, this is today. So I got two links that I need to share with you. One is right here. When you click on this link, it will allow you on your laptops to indicate who you are, and then you can download Mathematica if you don't have it already on account that IU has a license for the software. And of course, today our presentation is going to be in a notebook. So if you want to know the code, if you want a copy of the notebook that will be presented today, you can click here. Presentation should be only one. Oh, I'll fix it later. But in that line with the typo, if you click here, you get a QR code for the notebook. And that's basically all the things that you need to follow along if you want. So I'm going to stop sharing and I'm going to invite the main presenter to share the screen and get started. Is that okay?
Yes. Okay.
Very good. So please take it away. So
Okay, so like,
we also
hello,
have
everyone.
Two professors, Andrew Hansen and Amr Sabri, in the audience online, just to be clear.
Excellent. Thanks. We are basically like, part of Wolfram team. Like, three of us are here, like me, John, and Nick. And we are very happy, to be here with you guys. Like, the environment that you see, like, Nick is sharing with you guys is a Mathematica notebook. You guys have seen, like, the QR code, but like, I'm just gonna also like, put a few links in the Zoom chat. Nick can grab like, maybe like, from the second link, that QR code, like, just put it on the screen, like, so if people wants like, for the reference, they can just look it up and like, more details. So yeah, the second link is like, a notebook that we put together is just like, for the sake of like, see it as a like, a guideline. But what we do is a sort of like, live coding. Our plan is to have a discourse, basically a conversation between us. So, and we also welcome you to be part of that conversation. So at any point, like, if you have any question, please interrupt us, ask us questions. Our quantum project is 100% like, on GitHub, the open access and everything, like, the link is also there. So please, share with us if you have any feedback, like, if you, spot any bug or anything like that. And as Adrian said, like, here you guys at like, Indiana University, you have full access to all the products that we offer. So like the very top of like, that link, if you just click on that, you go like, and you can just use your university credentials too. So that's the only thing that you need. With the Indiana University email account, you can get like, Mathematica and everything else that we have, the part that Nick has highlighted. I'm just gonna like, the poster that you guys prepare, like, it's not like my name is very big, like, Johnson's nickname is much smaller. So like, I apologize to John and Nick because it was a, teamwork and their contribution much more than me. So like, my name, like, should be like, smaller fonts and theirs like, much larger. But I'll talk about like, the big picture, and then like, we will walk you through like, those steps. So we are gonna talk about quantum computation. We are going to focus on one fundamental concept. That fundamental concept is the concept of tensor, and then how a quantum computation resembles a funny, fancy graph that we call it tensor graph or tensor network. And basically, quantum computation is nothing but, some contraction on the top of that, tensor network. Within this process, like, when you want to do that, like, one interesting feature that we will discuss is going to be like, spiders and the connection with ZX calculus. So that's basically the big picture. So you guys should remember, like, it's a bit kind of departure from conventional things that you learn in typical textbook about quantum computing. It's more generic. We are talking about the generic concept, but like, you are going to reproduce all the results. So I'm going to hand it over to John and Nick, we are gonna have like a conversation, and we are gonna do a live coding. But please interrupt us, ask your question. We would be more than happy to have an interactive conversation.
Yes, as Mad said, please don't hesitate to jump in and ask questions as we're going. So the first thing that you might have heard of course, are about wave functions if you've studied quantum mechanics. Well, it turns out that those actually don't have a whole lot to do in the way that quantum computing is usually modeled, right? There's differences between continuous and discrete systems. So that's one thing to keep in mind. So let's first just look at like a diagram of what is a quantum state in quantum computing if it's not actually a wave function. So let's look at our plus state here. And so Nick is showing you the diagram. So in terms of like a quantum computing diagram, you might think of a state or an initial state as just something that has an output wire, right? So when we're talking about these diagrams, the wires are going to be things that are carrying quantum information. Maybe later we'll talk about the distinction between carrying quantum or classical information, depending on time at the end. And you can think of things that happen to these wires as quantum processes, and these are typically represented by gates, or more generically in an abstract sense, you can think of them as quantum operators. Okay, so here we have a state representing plus, which means if you measure the spin of something along some axis, you could get plus or minus. This is a system that has two possible states, at least in this particular basis. Now, one of the things that is interesting about quantum systems is that the basis is important. We're not yet going to talk too much about bases, but we'll get into that as we go on and what the connection there is with things like ZX calculus. So let's also, Nick, let's look at what the circuit diagram for a Bell state looks like, so that we can see the first thing that you've seen is a diagram corresponding to just one qubit, but the famous Bell state, you see there are two wires here. So there are two qubits in this state, and these are going to be qubits which have some entanglement between them. So actually, let me go slightly off of our plan here, and let's actually look and see if there's entanglement here in this state. I'll just put Nick on the spot here for a little bit of live coding. So if we take a look at this Bell state, we can see here's the thing in traditional notation that you might see in textbooks. And we can take a look and see, if we look at the state, that yes, in fact, and the function that Nick called here checks whether there's entanglement in the state. So one of the things that we've actually discussed a little bit is the difference between functional programming versus more setting things out as options. And so it turns out if you look in that link that we shared in the beginning, or that's in that QR code, there's a couple of different ways of getting the same visualizations that you're seeing for some of these circuits. You can either think of them as like a list of options that you're calling each time, or you might define something as a function. So here we have a function that it takes as input a quantum state. You'll notice actually, so Nick, let's not evaluate that Bell and see what happens in Mathematica if you give a function an argument that it's not necessarily expecting. So here, yeah. So here you see this quantum entangled Q function is expecting to get a quantum state as input, right? So since Mathematica deals with symbols, you can perfectly well write down the symbols that ask if this circuit operator is entangled, but that's not actually the right question to be asking, right? So if you want to see is the state entangled, let's go ahead and re-add in the two brackets that make the operator actually evaluate and turn into some state. So if we evaluate that operator on the what you might call the register state, which is sort of the default thing that goes into a quantum circuit, then you wind up with something that does evaluate to true. And now, yeah, so Nick is showing that there's actually many ways of equivalently getting the same thing, which is that, okay, so this is now the quantum state. And if we ask if there's entanglement there, we will get the result that yes, in fact, there is entanglement present in this quantum state. So
because you said that we are applying it to register state, but this actual circuit doesn't have any inputs. So when you apply it to the state with a register, it will actually increase the number of qubits. So
good point.
Yeah, so that actually is correct to apply basically to anything, to nothing, just a state with one dimension. That's what it's
Thank
running.
you about that. If I make, can you take questions now, or do you want to like?
Please.
Absolutely.
I was just confused about what you just mentioned, because it said 3 qubits in dimension 4, which kind of was inconsistent. So what was going on there? Oh no, dimension 1.
There may be some very weird things happening. Well, I can't answer why it's 44. Maybe there is some kind of bug here, but because usually, like this one is just a normal 2-qubit state, which is a register. When you try to apply the circuit that doesn't take any input, I actually don't really know what it's doing. It may be some kind of weird basis confirmation. Well, I don't know. Just consider it some kind of small
Okay,
bug.
no. So yeah, Bell should not expect any input. You're right. Yeah. Okay.
Yeah.
Right.
And basically, like, if you guys want to see, like, a conventional circuit, like, let's just look at, like, a quantum circuit that is called Bell circuit. Like, Nick, you can also show that. So this is like with all those wires, like, that was actually a good example, like, to distinguish. You see here, like, look at that diagram. You see the wires, it has input and output, and compare it with, like, the other one that had no input. So that's basically the fundamental difference between these two things. And in the common terminology of, like, quantum, many textbooks, like, you don't see these distinctions, but, like, if you want to do a computation in a good way, like, these distinctions, like, they become important. Like that operator is like input and output. The other one, like, on the top, like, as you see, like, it has only, like, 2 outputs. Like, that's the way to see that.
So let's then also look at something which has only input but no output. So let's look at the quantum circuit operator for Dagger plus. And here you'll see something that has information that goes in.
I can't type today.
There we go. So here we have something which is dual to the plus state. So remember, if we scroll up or if we just look again, the plus state by itself, we think of this as something that has no input, only an output. So there's an initial state that then goes into the rest of the tensor network. So here we have a state which is the dual to that, so something which has an input, but then doesn't go anywhere. So we'll see how this can be used as we get it more into other kinds of things that you can do with ZX calculus to represent things that might be going on in quantum circuits.
Just to be clear, the first one is a state, the other one is a test in ZX calculus terminology, right?
Yeah, that's right.
Yep.
Or
Okay.
state and effect.
Yeah, so if you look at the Bell circuit, that one has inputs. Then if you think the state generates an entangled pair, I guess you could say, put the circuit inputs 0, 0 all the time and encapsulate them like a battery inside the state, and the state will always emit that.
Mm-hmm.
So that's the circuit that becomes a state. And by the way, you guys are not drawing it from down up the way they do it in ZX. You're drawing it left to right.
Yep.
Okay.
There are different conventions, like, like some people, like, they put it at the bottom or on the top, like, some people, the numbering of, like, qubits, like, they start from 0 and then they go to n-1. For us, like, the convention, we start from 1 on the top, it goes all the way to the bottom. And then you would see, like, since we are talking about that, Nick, let's add measurements just to show them, like, why we are, like, going with that convention, because in Wolfram, and this is actually a very good connection with, like, ZX calculus, because when you look at this, like, this is a typical circuit that you would see, with the measurement, but, like, that wire on the top, like, in Wolfram, like, it's actually another quantum system, like, call it detector or call it environment. So if you want, like, if you look at, like, the diagram, that which includes basically, like, the other wires, you see, like, that's literally, like, what's happening. And basically that measurement later on we will discuss is basically like copy spider. So that's why, like, you see the convention now we are going from, like, 0. So zeros are, like, the one, like, the extra qubits that we add. And it's a much better, like, convention for basically, like, including, like, those extra qubits. And by the way, like, that show diagram is one example that John mentioned at the very beginning. Like, either you can add some options to the end or define a function, and those functions, like, they would take care of the rest.
Yeah, basically this is a special function for this presentation only, when we discuss the diagram with the specific styles. specific for spiders that they're gonna show up as green and red, as you'll see them. Yeah.
And the
And by the
dimension
way,
of the wire is also here, so that's going to be a point that'll come up as we go.
Yeah, and this is one other thing about Wolfram Mathematica and quantum framework, like those dimensionalities, they can be any integer numbers, right? Like, it's positive integer numbers. So it's not only qubits, it can be also qubits. So it's very generic, but I know we can also discuss it. Look at here, like, the one on the top is now 4 because you're doing like, 2 measurements. And the result is now stored in another quantum system, the detector environment, whatever you want to call it, because you have 4 combination, now it has 4 dimensions.
So if we actually just look at, what's the state that you get out if you take the quantum circuit operator where you measure the first wire and the thing that you put in is the state AB, you can actually see in traditional form what this is doing. So, so we've got our quantum state. So we'll do quantum circuit operator, just measure the first wire.
Not with them.
And then if we look at the state and specifically the Dirac notation for that, so if we
well, that's you want the actual
right, yeah, right, yeah. So if you're familiar with the traditional Dirac notation for these things, right, basically what we're doing here when we're measuring is we're correlating the state of the environment with the wire that's been measured, right? So that's exactly what one wants with a measurement is you're seeing the environment with some pointer going to one state, and the qubit is supposed to be in that same state when the environment is pointing to that state on your measurement device, right? So in terms of how we've modeled measurement, that's precisely what's happening right there.
And since we're talking about ZX formalism, let's just show on a spot, if we add a copy spider instead of that measurement. So just replacing that measurement by copy, so this is basically copy spider. And if we do that now, let's evaluate and look at the results.
That's already
So you see here, that's literally what is happening here. Of course, copy, it treats it as the typical quantum. That's why you see it has a different notation, but basically the take-home message here is the measurement that you see here, it's exactly fundamentally it's the same the copy spider. And you see slowly we are going in the direction that we are telling you that many of these operations, the tensor language is much more convenient, and you can have a family of these tensors to introduce different concepts. Now this is another spider that Nick is just adding there, and of course we can. This is a Z spider. Just for the sake of fun, let's also add an angle there for the Z spider because it can get also an angle there. And by the way, you notice the computation that are being done here, they are literally what we usually refer to either as exact or symbolic computation. This is basically one of the feature of Mathematica, all the symbolic calculation that you do on pen and paper, we can do it here.
So since we've gotten into a couple of examples of spiders, we can also do quite general spiders, right? So you can do the maybe, I don't know, simplest version of a spider. If we do a Z spider with a rotation angle of alpha, and we take a look at that, we can actually see that this is going to be the same as a phase operator where we do the same alpha. So we can actually take these two operators and we can then change this to a phase operator. So this particular Z spider is the same as an operator that you might think of using some other convention, right? And so in that last line, Nick has put in a statement asserting that these two things are equal, and we get the same, because really when you're talking about things that are happening at the level of tensors, even though the way that you might think about it or the way that you might have notation for it might be different, the tensors are actually equivalent here. And so when you have situations like this, you might not want to worry about what basis am I working in, what formalism am I working in. So as much as possible, we try to have support for when there are things that are expressed in different ways, but you assert that are these things in fact the same? You see, in fact, yes. So there's many different ways of representing these same concepts, and so as much as possible, we try to make sure that they're all easily accessible and you can visualize them.
One thing, like, it's just like, a common mistake that many people would do when they want to learn, like, this new language of, like, tensor-based, like, computation is many times, like, they ask, what is the corresponding matrix representation? And one thing that they forgot is that, look, when you go to the level of, like, metrics, like many of those information, like, you miss them, or like, another notation that is very common is Dirac notation. Like, for many of them, like, that important information is not there. So that's why, like, we usually tell our users, like, keep it the level of, like, tensors if you want to do a real computation, because the moment that you take it, like, to the next level, some of those information are lost. Maybe, like, the simplest that we can show is identity. For example, like, let's have an identity, but this time, like, instead of let's do something, it's trivial, but, like, let's say that, like, an identity that takes one wire, let's call it number 1 to wire number 2. So you see, like, this is a trivial operation, right? But if you ask, like, what's gonna be, like, the matrix representation of, like, this operator, it's identity, right? Like, it's trivial that this is identity. Like, nothing is strange there. Like, we can identity, but the tensor language is completely different. Like, when you go to that level, you're losing some information. And this is, like, one thing that, like, people, they have, and by the way, like, Nick is showing identity in higher dimension, for example, dimension 4. This is the thing that, we always remind, like, that researchers or, like, students that, like, it's like one thing that I tell my students is, like, going to Italy and you should learn Italian, okay? Don't speak English with Italian, right? Like, and that goes with any other countries. Like here, like, the language, the correct language is tensor language. So focus on that. Do not enforce what is, like, the matrix representation, what is the Dirac notation. They help, but you would reach the limitation very fast. You would reach, like, the limitation that you would say, no, it's not gonna work. I should adopt, like, the other language. Like, for example, like, let's have a very simple, Z spider, but Nick, this time add, I don't know how many input output, add, I don't know, 3 input, 2 output, whatever you want, like, your choice. I see here, like, this is something that you really need to understand it based on, like, the concept of basically, like, tensors. Because if you want to reduce it, like, to the previous one, like, it doesn't make sense. Because, like, the output inputs, like, they are different, but the matrix representation is like the very special case, the same number of input, the same number of output, and the dimensionalities add up. So that's a side note, but very important side note that, like, users should remember.
But so question. So fair enough. I mean, I certainly would agree with that, but do you like, how can you explain you have to be able to reason at the level of, the tensors. So do you have automatic support for that? I mean, transformations, rewrites, can you simplify? Can you normalize? Can you prove equivalence of things at the level?
So the answer to that, like, let me just, answer it in a generic sense, but then, we are gonna go back to, like, the ZX formalism in particular. Like, one of the very unique feature of, Mathematica is its tensor functionalities. spatial, like, symbolic tensors. Like, this is so unique that, like, if you look at, like, most researchers using, like, those type of calculations, like, they're, to go, like, tool is Mathematica. So there is a very strong support for any tensor manipulation. For the very specific case, yeah, like, let's, I don't know, like, maybe John is gonna be like, a few steps ahead, but do you want to jump directly to the circuit? And
yeah, I think let's start with the GHZ circuit. This might be one example where we can show some of these simplifications that can happen. So let's do quantum circuit operator for GHZ. So you see that the default thing you get back is in terms of the representation in terms of gates. But if you want to look at just the raw tensor network, let's just look at the tensor network of that GHZ circuit. And let's also show the edge labels there so that you can see the indices. So here, this is more of how we're representing the tensor internally, so that then when you want to actually evaluate this tensor network, you can contract the indices in some way that gets you a.
And that's basically like, yeah. So and this is practically like, what you see here is a tensor representation of like, GHZ state. So that's literally like, that tensor representation. So in that tensor language, like, let's see like that contract tensor network. What is happening here is tensor contraction. Now you're in the business of like, okay, how we can do tensor contraction. Now, what is special about like, ZX calculus is that for tensor contraction, there are some tricks. I don't know, like, sometimes, I personally call them like, shortcuts. Like, you don't need to do the actual computation because you do it one time and you realize, oh, there are like, simple relationship when you want to do like, tensor contraction, like, between different, like, tensors. For example, like, Nick, let's look at like, ZX tensor network, just to remind our users, like, ZX diagram is actually like, another tensor network. Now, what is special about like, this tensor network is that, and this time let's also add like, the edge labels just for clarity that like, this is. So each like, basically like, the way that you should read it is each of like, those vertices, it represents a tensor. Each of those edges, they represent a contraction that should, happens between them. Now, either you can brute force, like, okay, like, I just want to do tensor contraction for simple ones, like, no problem, you can do it. But we know that like, the dimension usually, in quantum, it happens exponentially. So you always need a more sophisticated, bare way, optimal way of like, doing those tensor contractions. What is special about like, ZX formalism is many of them can be done like, basically based on just the connection between like, those basically angles and the color of like, those vertices. Like, you don't need like, look at those two like, green, vertices at the bottom. Like, there is a very simple contraction between the, indexes, 3, 1 and 5, 1. And like, you can easily like, like, how that contraction is done. So the way that, the common terminology in ZX formalism is, do the fusion. And, let's just do the fusion and let's see what happens.
So we set the option fuse goes to true.
Yeah.
And
basically, like,
yeah, sorry. Notice that there's some permutation of where things might show up in the diagram, but those two green vertices are now right there turned into one green vertex. Mm-hmm. So we've in this particular circuit, there is only one fusion that gets done. And so this is the fusion step. But it's not the full simplification that one can do. So you can control which parts of the simplification you might want to do. Do you want to only do the fusion part? Do you want to fully simplify things? So these three tensor networks are equivalent in terms of what they are actually going to give you when you go ahead and do all the necessary contractions so that you get something concrete out the other side.
Mm-hmm. And the beauty of like, ZX formalism is, Nick can speak to those details, like, he knows that much better than me, is The contraction, like, you can do it like, I guess, like, using, in Wolfram language, we usually call them some replacement rules.
Well, you don't do contraction using replacement rule. You mean the rewriting of the X diagrams themselves?
Yes, rewriting rules. Sorry,
Yeah.
like bad terminology.
Well,
So
as of right now, we don't do anything rewriting ourselves because it's like
yep.
a very complicated thing and it's like a research topic. We just right now just underneath is just some Python libraries that doing those fusion and simplification of the X diagrams. But we have some, if we're gonna show, maybe if there's gonna be some time, I can show some work of we can actually make some complicated expressions corresponding to each of the X diagram and actually write them using Wolfram language, almost like explicitly just use the expression, symbolic expression, and rewrite it using the rules or axiomatic equations.
So can you guide like use Mathematica here as a proof assistant kind of thing? Like, can you actually guide it and tell it to try this, try that? Like some of the proofs.
In a way, it's possible in theory. It's just not very well developed right now.
Okay.
But yeah, we have like underneath we have already some nice automatic film prover, right? To which one you can just feed a bunch of axioms in terms of equations, and you just need to specify those Venn diagram rules in terms of those equations. And then as soon as you reduce this kind of diagram into an expression, you can then basically simplify it. How the usual Wolfram language expression are being simplified, like integrations, differentiations, all of those polynomials can be simplified. In the same way, given some equations, you can simplify as the X diagram expression. And depending on which actual equations you will feed it, you can control it. But
And this is
it's
like,
very early right now. Yeah.
and this is one of those topics that, like, we are actively interacting, like, with academics, like, literally all over the world, like, because we know that, like, it's a hot topic, but given limited resources that we have, like, we know how to do that. It's just like, some of the heavy liftings we are looking for, collaborators and, like, joining forces with academics. So that's basically hardcore bleeding edge of, like, research on ZX formality. Now, since, like, we showed, like, this example, like, maybe one fun thing is just, like, for, like, maybe people who are kind of new to this topic is, if I may suggest, like, John, what do you think? Like, going through some named spiders, like, a family of, like, different spiders that we support in Mathematica.
So I think the permutation one actually was one that would be good to show, because before, we showed that you could have some identity operator that it's not changing any of the state information, but it's switching what wire the thing is on, right? So you might have an operator where you do a permutation on the cycle 1, 2, 3, for example, right? So if we take a look at that, we see another case.
Cycles.
So, yeah, cycles 1, 2, 3.
No.
Well, that is also a permutation, but yeah. So here you see this is another one where it matters that you're representing things as tensors rather than just as matrices. So another thing that we might show, we had the example of copy earlier. So we also have cup and cap, which are sort of unique ones that can be used if you are wanting to represent things that don't have a particular input or output, right? So one actually interesting exercise that you might go through is you might think, well, how does this ZX formalism relate to the typical computation that you might do on hand if you were just doing partial traces of some density matrix, right? So here in the CHSH circuit that Nick is showing, here we have this cup representing the initial Bell state that goes in. So the CHSH game is a famous example that shows how quantum strategies can outperform classical strategies if you're trying to accomplish some particular task as the result of going through a circuit. So if you want to start with, let's take a random pure state. And then if we take this pure state, and then let's do like a quantum partial trace over a circuit where we're starting with this pure state. So actually, I guess let's show the circuit first. Let's do the pure state. Quantum circuit operator. So yeah, pure state. Let's measure that first wire and then do an identity operator on the 0 wire, just so that we can show.
Let me do this.
Yeah.
Maybe let me just copy paste it. Because I have.
Sure.
Do you mean this kind of thing?
Yeah. So if we build up to this, right? So I was going to go through this sort of more slowly, but if we want to show a circuit that implements what you would be doing with pen and paper, if you wanted to start with some pure state and then do a partial trace representing projection operators that are doing some measurement. Mm-hmm. This is a circuit that is made out of spiders plus the states that are you're seeing right there on the wire 1. So this is going to accomplish the same thing as though you were doing the partial trace on pen and paper, right? So let's take this circuit operator and let's run it so that we can see what the outcome is going to be. And if we look at that, now you'll notice this has been doubled. So this doubling and undoubling is another concept that is used a fair amount in our quantum framework. So if we take that result that we have right there after running the circuit, and then we undouble it, you can see something that looks much more like you're expecting with a density matrix. So all the same information is contained in either of these representations, but this idea of doubling or undoubling how you're representing the information and what's going on in terms of the tensors is something that you might care to reason about if you're going and learning about this formalism. So another example, so instead of
let's just
circuit, yeah.
John, let's just pause for a second. Nick showed that complicated circuit, just for the the diagram. I mean,
Let's break it down.
Okay. So basically, step by step, what do you do pen and paper? You create the density matrix. We know that density matrix is literally I guess the visualization is very similar. And now, you would say that, okay, now, I want to do some sort of bringing that into the outputs. I want to look at the the results. It's now that pipelining that Nick is doing, and then you would say okay, now let's do some measurements. And the measurement you see that you would do on the input wire, output wire coming from your state, that's copy spider. So that's one thing, again, maybe one important take-home message from this, I want you to remember that literally what we call as measurement in typical quantum is a copy spider, which is basically the Z spider. Okay, so that's the way that we can understand it. But in quantum, as I told you, they don't show you the information is just stored in that quantum system on the top. Okay, they just show you that double line, which is basically, they call it classical wire. And you can do the same with the other wire, the wire that you basically twist it and you bring it there. And of course, then as Nick said, the last step is do the partial tracing. So you would say okay, how I can do the partial trace? Those wires that you don't care, just put a cap. You see, look at the labels on the left, it's 0. I guess it's the one that we have is 0 and 3, maybe just to follow the same, exactly the same thing, 0 and 3. You see, we created what we do on pen and paper. Of course, like, this is a trivial, example. You may say, gosh, like, really, like, just creating the density metrics and do all the partial tracing, etc. Like, with the language of, like, spiders, that's such a complicated thing. So yes, that's how it's done. But there are different ways, like, as John said, the very concept of doubling is a compact approach to do exactly the same calculation.
Another way to do the same calculation. So let's take a quantum circuit operator that's just the state, and then let's double that, and then let's measure after we've done the doubling. And then let's use your show diagram function so that you can see the dimension of each of these wires. So here, notice the dimensionality of the wires is important. Since we've used the doubling, and then we have something corresponding to measuring, notice that after the measuring, the dimensionality of the wires is reduced. And so this gets into another perhaps abusive terminology, right? Where now if you look at what's in those two wires, the amplitudes are going to correspond to the same probabilities you would get as though you had measured the first wire in that initial diagram, right? So these diagrammatic ways of representing these things, you can get into different conventions for how you're going to do it. But it's also interesting to think, at the level of tensors, are these two things really the same? So do we still have our GHZ circuit with a variable name? Because if we do, we could maybe take that, and if we look at what the
this is the conventional quantum.
Yeah. Yeah.
This is conventional quantum. So, like, Nick just evaluate that less, they would see the famous GH state, like, on the register, like, so this is typical example. Now, let's do the contraction of, like, the ZX tensor network. So it's gonna be like, first, let's go with ZX, like, just show, like, that they are the same ZX tensor network. And then let's do the tensor contraction here, which is practically like, doing a fusion. And, like, the claim here is like, look, this tensor is exactly the same as, like, the tensor representation of, like, the thing that you see on the top. But there's minor subtlety here. And that minor subtlety is, like, when you work with, like, these, spiders, remember that, like, there is always an overall factor, like, that you need to basically, you see here, like, the pipelining, like, in this case, there's a factor of 2. So, for example, in Mathematica, if you want to compare them exactly, like, Mathematica will throw an error message to you. They will say, oh, they're not, the same. I said, gosh, they should be the same, but just look at that. Because of that, factor, 1/2, there is a difference between them. So that happens a lot with the spiders. Like, Nick just showed, like, the Dirac notation of cup spider, which is a Bell state. That's another example that, like, that an overall, like, normalization factor is different. You see here, like, that famous, 1/√2 is missing. For those of people who are new to quantum computing, I totally get it. Like, it will take, like, some time to basically make your peace with this new language. And, like, sometimes, like, people, they are not convinced, like, oh, why I should go in this direction. High-end researchers, like, they would see, like, the benefits immediately. Like, oh gosh, like, I'm gonna be in the business of, like, translating a quantum computation into something else, and then, take care of that. Given, like, we have about 15 minutes, so I may suggest 2 things. We have more content and we can, like, elaborate more details, but we would like to hear some questions from our audience. Like, shall we go into more, like, detail, or, like, more, like, examples? Like, give us some feedback, and then we can, decide, like, what to do for the next 15 minutes. And of course, we are completely open to Q&A.
Yeah, so one thing that perhaps we'd like to see is what I think was mentioned earlier. Let's say you start with a circuit for teleportation, and then you do, which is a traditional example. Can you keep simplifying it automatically up to the point where it becomes just one wire? Or if you were to say, for example, you showed us for the GAZ, you showed us the tensor networks. Right? If you look into the various papers, I think John von Wettering, I forgot his name. That's one example that he goes through. You take the circuit, you convert it to ZX, and then you start simplifying it. Where at the end there are just 3 wires coming out of the of the one thing that is the, I guess, the state. Could you show us some automated transformations whereby the simplification of the circuit happens?
So let's see, like, what are the good examples? Like, would it be like, let's see, like, connecting now.
Can I show you something? I take the screen a little bit. Let's just go randomly, not randomly, but didn't anticipate to do this except now. Hang on just a second. I'll show you what I mean. So if I go, let's say, Xanadu, ZX, calculus, penny lane, and I say I want to see an example, and I go over here, and the first thing that I see on this side is this animation. Now, clearly, this is made up, right? But would you be able to build something in Mathematica so that Mathematica would then take over? You know, like in Wolfram Alpha, you do little exercises in calculus, and they show you all the transformations up until at the end in calculus, regular calculus. Would you be able to do at this stage in Mathematica something like this?
Well, in theory, yes. It's not
Oh, I see.
ready yet for. Maybe I can fetch some example of how it can look like.
So okay, that's under development, as far as I understand. That I understand. What is the relationship between PYZX, which physics, and Mathematica? Like, is one of them? Are they at the same level of development, or you have no idea what stage these guys are in? Just if we were to compare tools, are you far more advanced than them, or just about as them, or you have no idea?
So in terms of, go ahead.
Currently, it does all the simplification steps that PyZX should do, right? So as long as, I mean, the thing I think that Nick was referring to that we still actually probably would want to do would be showing these step-by-steps, right? Because currently you can either simplify or not, right? Where it's either there's a true or false. And as long as the the simplifications are something that are doable in a reasonable amount of time, you'll get the simplified version as far as PyZX does as well, right? And Nick can actually probably comment a little bit more detail about the relationship between what we are doing under the hood in order to simplify these ZX diagrams in relation to other tool sets. So if you're wanting to show each one step by step in terms of
kind of like on the screen right now, that's the GAZ, slightly different. And then it says first you convert, and that's the first thing that he shows in his paper. And then it says, then you would have to do this, which he can do because he knows, but would there be any way to say Mathematica, or maybe in the future, I understand, could embody these transformations so that at the end you have the simplest possible circuit that you could possibly have, given...
This is pretty similar to graph rewriting rules that actually get used for a totally different purpose, right? So actually, our implementation of the way that the simplifications are done, actually, as Nick said, doesn't currently use rewriting rules. But if we were to do an implementation that used the rewriting rules, then yes, that would be doable in principle, one step at a time.
Okay, so you can take the screen away and show us whatever you want. Anything is good.
I can show you a sneak peek because you're so interested.
Excellent.
How it should work in the future, not right now, but in principle, right? I already showed you how you can get this expression for this GHC example, right? You can see my screen, right?
Yes.
Yes, we can.
Okay. Yeah. So given this expression, it's like I have this little notebook over here. You basically, what I need to do is like specify all of these rewriting rules in terms of this equational logic with this kind of expression, tensor, identity, inputs, outputs, and all that. You do it for tensors, all of these fusion rules. You basically get everything expressed as equations, right? Given that equations, you treat it as some kind of axiomatic theory, equation on equational logic. Here I have like a small example of a simple fusion, for example, right? But not as a simplification, just as a proof. So I already know what the result is, right? I know like this is some it's hard to read, but this is some Z spider and another Z spider, and here they fuse and their phases increasing, right? And basically this is just the theorem that I want to prove. I have this list of axioms, which I call suppose X, and the small version of it, and you can just run some automatic theorem proof on it, you get this proof object, and there's like a complicated proof graph underneath. It's like there's a lot of steps happened, but you can also rewrite this proof sequentially, as just trace it over and just get the actual path from left-hand side to the right-hand side of this theorem that you're proving. And then you can show all those transformations like continually as a nice animation, right? You just render these expressions as the X diagrams again. Maybe try to preserve the continuity between spiders, and you'll get a nice transformation just out of the box, theoretically. That's the plan.
Nick, you can also probably comment on this timing detail better too, but my understanding is the reason why that's not the current implementation is that that's likely to be quite a bit slower in terms of runtime than the current implementation. However, if you want to actually see the step-by-step, it's nice, and that's a price that one might be willing to pay. Is that a fair summary, Nick?
I'm not sure if you already are able to reduce it, you certainly have the steps, right? Because you actually have to do them. So you can store them, and because I don't know what specific direction PySX, for example, is taking in order to perform those rewriting automatically. Maybe there's a bunch of heuristics, maybe there's something cleverer than that, right? So right now I'm just planning to do this automatic theorem proving thing first, and then PySX is just going to be our reference because there's much more research happening on that front than there. So.
For example, like Adrian, that very specific example that you showed, like a different version of like GHZ, like which has the Hadamard on the second and two C nuts, like as we were discussing, I quickly like tested on, for example, PZX, and even there, like the fusion that is done is not to the full scale of like what is happening like on that paper. So the take-home message is this, like this is doable. It is ongoing, like project, like the notebook that Nick is showing you. But if you want a full automated like formulation that does basically fusion for any case, not only a spatial case, okay, like basically like that replacement rules that Nick has at the very end of that code, like that's the headache. If you narrow it down into something very specific, you would say, look, I only have this case or I only have that case. It's doable right now. But if you want something, the most generic case, no, it's non-trivial project.
I understand. And so, but this was very useful, and I thank you so much for showing us. My point of view is slightly different. I want my students to be able to do this by hand for small circuits. And then at the end, I want them to confirm that what they did is in fact correct by running it in Mathematica. So like I want them to calculate integrals, but then at the end, I want to show that if you do it in Wolfram Alpha, they give you roughly the same steps, just as a measure of confirmation, confidence. So when Stefano
the confirmation step is relatively easy because you have the initial, so just put it in like Mathematica, and you will get the final tensor. Okay, so that's the expected result, like because we know we do the contraction differently. Then you do the fusion, you will get a different tensor network, a simplified version. Then put it in Mathematica, and then just compare the final outcome. Like basically like it's let's see what is the best way of like Nick, did you get like, what I'm suggesting here? Like, it's
Yeah, like almost exactly what we did when
yes.
when we were comparing circuits like that. You just
Yeah.
made not for a single operator, but the whole network. You have two different circuits. They contract. This if you expect that they're the same, then the contraction the same tensor is going to be produced, and we can just compare them up to some phase factor, maybe the global phase.
Yep. Yeah, that's literally like, the which is doable right now. It's just like, uh, to the level of like, fusion that we are supporting right now, it's primitive. It's not basically like, let's show it like, we can even show it right now. Like, take one of those tensor networks, like for example, that one, and then do the contraction, you will get this result. Okay, so this is basically what your student will get after doing simplification and contraction. Then don't do that. You see, these two are the same. If these two are the same, it means like, the fusion and simplification done by the student was the correct one.
Okay.
Yeah, in other words, showing the steps is actually the very non-trivial part here, because it involves all of the rewrite rules. You know, the way that the tensors are being handled under the hood is a bit different than the, by hand,
Right.
what you would do on pen and paper, right? And so that does allow you to check the final outcome, but being able to see the step by step, specifically using the ZX calculus, yeah, I mean, you've seen the sneak peek.
But that could be like, Adrian, like, it could be a very simple mathematical function. Like, separately, let's discuss together. Like, it's a nice problem. Like, even it could be like, a mini project for a couple of students. Like, it's a simple construct, but it's very useful. Basically, you have the like, given like, ZX diagram, they simplified. You want to make sure these two are equivalent. Like, you can do it under the hood exactly what Nick is showing you here.
Another very non-trivial thing about showing the steps is that there's many different paths that could get you to the same end result, right? And so, being able to in a useful way show all those different paths based off of what the student might be doing, that's a much more difficult problem than just checking the end thing that you get is the same, right?
Yep.
So some of this we do in summer. For example, we have a class, and the thing is that people who come in, they don't have a tremendous background in anything except maybe some programming. So this is a 200 level class. And one of the questions at some point before around midterm is, here's a circuit, here's another circuit. Are they equivalent? So the simplest thing that you can do, you go put them both in Qiskit and you say, what's the matrix for the circuit? Are they the same or are they not? If they are the same, you at least know that they are equivalent, and you could start proving that. But see, people who are saying, I'm totally lost, I need some clue, then they can run Qiskit and get the matrix, and they say they are or they aren't. And then the rest of the thinking comes in, like why? And then so we use the Misty States formalism to trace what's happening inside, because we want to use many different techniques. But understand what you're doing, and this seems to be really useful. Thank you for showing it to us today.
Do we have any other questions? Because we do love audience questions.
So, Dimitri, do you have a question? You can come over here and ask. He's gonna come and ask you. You put microphone. You just come in front. Yeah.
As they are doing that, Nick published this notebook and show the QR so they can access the notebook too.
Yeah, I'd be curious to see an example with QDITs, and just also how I mean there was some of it, but how composition works for building up larger circuits. I'd also like to see how that works out.
So like, the case of like, QDITs, do you want to see it like, as a spider or like, just in general for any quantum circuit?
Either would be good.
Okay.
Yeah.
So by the way, like, this is a QR code of like, Nick, like, the notebook that he's just showing you. So like, you can get it from here. So let's go with like, the simplest case, like, let's have a quantum circuit Nick, apply, I don't know, like, you know, X, the usual poly X on the first wire, and then go with the generalized poly X in 3 dimension on the second wire. Now let's look at the diagram and, like, you know, just show the diagram, just making sure, like, you know, people, you see here, like, you know, that's why, like, you know, we have that function, you know, that for this presentation, you know, initially you don't see the dimension. So this is a circuit that you have poly X acting on the first, and then the other one is also poly X, but I don't know, like, you know, if you're familiar, this is what people call generalized, like, you know, poly X. And now, like, you know, if you evaluate that circuit just to show the dimensionality, like, you know, they can see, let's apply it on the corresponding register state. You see here, you have 2 QDITs. And of course, like, you know, the dimension here, just show the dimensions there, like, you know, you see is 2, 2, and 3. So, like, you know, it's like, you know, a different dimension. Of course, you can also do it with the spiders. Let's have a, I don't know, a general spider, like, you know, that's why, like, you know, we love a generalized version of a spider in our framework. And I think, like, you know, the good example would be Nick, you know, I don't know, let's go all of them with, for example, like, you know, with, you know, dimension. Yeah, what they're like, you know, now he's doing something fancy there. Now let's do it, and then we are gonna look at the.
Is it the correct one? No, it's not. Somehow it's not constructing it. Okay, that's
Yep, that's the correct one. And let's explain what is happening. So look at here, this is a simple spider. This is like measure, but in a much more generic sense. The input, it has a dimension 5. The basis of that input is generalized poly Y in dimension 5. And then the output is generalized poly X in dimension 3. Like, you know, if you want, like, let's show the, you know, the Dirac notation. I know, like, you know, maybe it doesn't look very nice. Do we have this one? Do you think, you know, the Dirac notation will help? Let's see. No, Dirac notation is very ugly, huh?
probably it is.
Yeah, it's like, you know, let's simplify that. Yeah, you see here, like, you know, these are basically, like, you know, the representation of that spider, but this time those X and Y that you see, they are in for QDITs. They are in higher dimensions.
Yeah. That makes sense.
This is another reason why Dirac notation is sort of not the native way that these things are represented in the language, right? Is that you know, Dirac notation has a horrible abusive notation problem, which is that when you're just looking at a bra or a cat, there's a lot of implicit information which is there, right?
Mm-hmm.
You know, if all you were looking at was that thing in Dirac notation, I mean, how are you supposed to know that there's not, you know, this is actually dimension 5 in X and dimension 7 in Y, right? If you just look at the bracket notation, there's no way to know that. So this is why, you know, the representation of the things at the level of symbols can't just be bracket notation, right? Although you might want to see it in bracket notation to compare with things that you've seen in textbooks, but you need more information to fully specify these things.
Yeah. I put another example, like, you know, in the Zoom chat, Nick, like, you know, maybe, you know, less complicated, like, you know, it shows the case of, like, you know, 3 dimensions, and just look at the Dirac notation. Maybe it is more familiar because everything is now in dimension 3. Okay. So you see, like, you know, you remember, like, you know, it was always, for example, like, you know, 0, 0 and 1, 1. Now, like, you know, since the dimension is 3, now, like, you know, it's different. And now, like, you know, you can change the basis. Like, you know, you see Nick is changing one of the bases to poly X. And if you look at the Dirac notation this time, you see one of them is, like, you know, X. I personally, like, you know, always had a hard time, like, you know, looking at the Dirac notation. That's what, like, you know, Nick's design is. When you evaluate, for example, that animal, that operator, we show you a summary box because that summary box contains much more information, just showing you, like, you know, that Dirac notation.
Yeah, that makes sense. Yeah.
Great question. I feel like there was a part 2 to that.
Yeah.
The first.
Yeah, it's not. It's like a separate question, but what composition?
Oh yeah, composition.
Like, just as what a super simple example would be is having one function or whatever which prepares a state and another which teleports it. What would putting those together look like?
So the composition, it will be exactly the same like composition in Mathematica.
Yeah.
Like, the only thing is like, just keep that in mind, like, that quantum thing, like, like if you apply the like state on an operator, it's a strange, composition, but operator on a state is, a good composition. In our framework, like, all of them, it will be computed. Like, you remember the very first example that Nick showing you with the bell and that 175 is strange dimension. So the computation is done, but like, it's gonna be a strange. So the composition, I don't know, like, Nick, do you want to show us a composition of many different things together? I don't know, like, go with the circuit, add measurement, add quantum channel, noise, like, whatever you want, like. So this is like, literally the composition of like, completely different thing that is happening here. So you have like, bit flip, which is basically a noise channel. You may ask, oh gosh, like, why noise channel is connected with another quantum system? That's literally like the environment, right? We would say the environment is influencing your quantum system. So that's the environment, like, the qubit 0. And the negative one is the detector that is interacting with that wire. So what you see here in our framework, this is literally the composition of like, those different things. And then just to make it, fancier, like, I don't think like, it is experimentally accessible. You can do something with the 0 wire, like, Nick put the CNOT at the end and then manipulate, I don't know, which one you want to manipulate, 0.
Let's do the measurement. Yeah,
let's do the
say
measurement.
Yeah.
Because for the bit flip, it's very noisy. I don't think like, it is experimentally accessible, but if you do it on measurement, this is what people would usually, for example, IBM people, they call it the dynamical circuit. So that's how you can define if or like, other like, conditional like, operations given the measurement result. But the CNOT in the middle, I'm not sure if it has any experimental counterpart. It's saying that the noise that is responsible for that bit flip, you have access to that. It's maybe it has experimental counterpart, but I don't know. Like, it's not obvious for me.
But at the level of tensors, you can do it, right? And so then it can be represented at the level of tensors. And if you're tracing over that environment channel in order to get the final probabilities that you'd expect, this is how things are being represented so that you can have noise channels, right? Is that it's another quantum system that gets correlated with part or all of the circuit, and then at some point you trace over it.
Yeah. So it looks like the operators, and I might be misunderstanding. It's been a while since I've used Wolfram language, but it looks like the operators there are strings. So if you wanted to define an operator that itself was a composition and then use it within another composition, how would you go about that?
Well, you can define operators simply like that, right? Because here in this wrapper of the circuit operator, you use the same constructors, but you can construct operators independently of the circuit, right? And then you can, if you have those operators, you can also compose them together. You can, here's like take this one, just apply one to another. You get the composition.
I see.
Right?
Yeah.
You can change wires. This X1 can be some weird. It can maybe go from 1 to 2, or maybe not like that. Yeah, I think you need to put some lists here. It's like now it takes the first qubit as an input, outputs it on the second one. We can still compose it with a CNOT.
And of course, like in a quantum operator, you can have any matrix or tensor. You don't need to go with the named one. Like, I don't know, like, whatever you want to put there, like, that's
basically something weird like that. This wire goes like in some void. So it's a little bit weird, but it works.
Okay, that makes sense. Yeah, thank you.
Yeah, and let's also maybe show, let's do quantum operator of the representation is some random 4x4 matrix, and it's represented in poly Y, right? So if we take that 4x4 matrix, yeah, so let's do random real. Now this isn't necessarily unitary, right? Because we've just done some totally random one, but you see as part of the summary box, this is telling you, hey, this isn't a unitary matrix, but if you want to use this as some kind of strange operator, you're allowed to do that symbolically, right? You can do the computation, and if it's not unitary, then something funny might be going on, but you can certainly do it.
Yeah. Cool.
And then as the second argument, quantum operator there, let's do that's the representation in the Y basis.
Why?
Why?
Yeah. You see, like now it's
different. So you see, yeah. So the point that we're trying to get across here with this particular example is that if you know the representation of the operator and you know what basis that representation is in, that's how you specify some arbitrary operator, and then you can use that. So when Nick has been showing like quantum circuit operator of these strings, you could also use this operator in the list.
Yeah.
So I don't know. Let's maybe put this operator in. Yeah. So that's part of a circuit that then has some other more normal operator maybe.
Yeah, that makes sense. Thank you.
Yeah.
That's about it for me, but thank you very much.
Sure thing. Any other question?
We don't have any other questions. This was very useful. Like when we go over Grover search, we give names to portions in the algorithm, and then we use them, put them together. So that's why I think the question came about. But this was very, very informative, and thank you so much for your time. And I guess we have another meeting in the morning, right?
Yes. with you only, like, I wish, of course, like, that, like, that feel free to contact us, like, the link that Adrian shared on that web page, like also here, like, the easiest would be like, the quantum@wolfram.com. So that's also the email address. So feel free to contact us. And, you guys, you have, full access to all Mathematica products. So we would be more than happy to help you with your research project or educational project.
Yeah, so we use Wolfram Alpha already in the summer course. And I'd very much like to start using portions of this as I introduce the quantum in pictures thing, to just show that support for that is being built and will soon be complete and so on.
Yep.
So this is very good news, and thank you so much once again for your time.
Sure thing. Of course, like, one fancy thing, like, it is still in progress, like, bleeding edge of technology. Maybe John can show you another time, is we have done a lot in terms of, like, large language models and, like, coding. So right now you can go and, like, call, for example, get the help of ChatGPT to do all the coding and, like, in Mathematica, but that's a different story. Like, another time, like, we can show you, and, like, it would be less heavy in terms of, oh, I don't know coding. No problem. Use LLM or ChatGPT to help you. This is literally like, you see in one click, Nick is showing you. Now you can activate that and you can start, like, interacting with, like, LLM.
Let's also maybe do Control S, or excuse me, a Shift tilde, maybe some point above that. We're going to send that entire context. It's going to take forever.
No, let's try. Yeah. I want to try.
Basically, like, Nick is okay. You see, maximum token, too much.
Nick has attempted to send his entire notebook, right? So you can manage the context by putting in these sorts of things. And
okay, it's smaller. Let's see, like, Grover and etc. Quantum framework for life. Okay, good job. You see here, like now it's like ChatGPT is telling you what is happening here.
I'm gonna purchase the Wolfram language cards that came out last week, and I'm gonna use them to give to students when they have good exams, grades, whatnot. They get that as a prize.
But by the way, like one side note, remember, like whatever LLM you are using here, like behind the scenes, so like payments as everything, like it goes to that one, like hopefully in near future, like Wolfram would offer like our own native like LLMs, but this one is OpenAI, right, John?
Yeah. If
Yeah.
Nick, if you go to the the thing, and you go to models, right? You see that if you have API access to either Anthropic models or Palm or something like that, you can pick those. But also, if you've got access to the Vision preview and things like that, you can use Vision.
Sure, I have them here. This is Dimitri with the cards. These are the cards
Nice.
from several years ago.
Cool. But anyhow, like this is yet another like this can be done in much fancier way, like so a different topic, like I don't know, like if there is any researcher or students here who is into like ChatGPT and like for research and education, very hot topic. And like we are very proud to say like Wolfram is also one of the pioneers on that, like we are interacting with people. For example, you see here Nick is using ChatGPT to explain that circuit, what is happening there with that Grover circuit. Does it call it like oh no, like that's nice explanation. And that's correct. Doge, Jozza, Grover, Fourier transform. Yeah. Not bad.
It does do a surprisingly good job if you show it pictures of it could be quantum circuits or could be other just plots of some flux versus energy on some like one-dimensional quantum system, and it can do a pretty good job of picking out what the system was just based off of what the plot looks like. It's kind of surprising that it can do that, but it's surprisingly good sometimes.
So just to wrap up here, remember guys, you guys at Indiana University, you have full access to everything that we showed you here. The only last exception is if you want to use ChatGPT, you need your API key from OpenAI. So the last piece was independent from us, but the rest of like, all the functionalities that you see here is available for free at Indiana University. So use that.
Thank you. We will. I mean, we are to some extent, very free. Well,
any other question, anything else, like,
no, that's it for us tonight. Thank you so much.
Excellent. Thanks everyone for the opportunity. Thanks, John. Thanks, Nick.
Okay.
Thanks, Matt. Thanks, everyone.
All right. Thank you
All
once
the
again.
best.
We'll see you. Stop recording now.